Oxidation reduction reaction is going to be the topic in this first lesson on a whole chapter on oxidation and reduction. Now, these oxidation reduction reactions, aka redox reactions, are simply electron transfer reactions. And in order to keep track of who's gaining electrons and losing electrons, we're going to need to learn to assign what are called oxidation states, kind of analogous to an element's charge in a compound and things of this sort. So we'll go through all those lovely rules, we'll work numerous examples, and we'll learn some lingo associated with these oxidation reduction reactions. Now, this lesson is part of my high school chemistry playlist. I'm releasing them weekly throughout the school year, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. All right, so oxidation reduction reactions, these are pretty ubiquitous. They're all over the place. So in fact, everything in dealing with your metabolism is typically an oxidation reduction reaction. So you are exhaling carbon dioxide because, you know, when you metabolize your food, you're actually oxidizing it, turns out. And if it's getting oxidized, it turns out oxidation always comes with reduction, as we'll see based on their definition. So before we deal with this lovely reaction, just get some lingo out of the way here. So oxidation is simply the loss of electrons, and we often come up with a couple of different mnemonics for that. So Leo, lose electrons, oxidation, or OIL, oxidation is loss of electrons. And then we've got reduction, and reduction is the gain of electrons. And so we've got GER, gain electrons reduction. So you've got Leo the lion says GER, one way to remember a mnemonic. Or you could also say RIG here, and OIL and RIG go together nicely as well. So reduction is the gain of electrons. And so whether you go with Leo the lion says GER or you go with OIL RIG, doesn't really matter, but you do have to definitely know the names or the definitions of oxidation and reduction. So again, oxidation is the loss of electrons, reduction is the gain of electrons, and the reason we keep track of this is, again, these redox reactions are electron transfer reactions. One species is going to transfer electrons to another species, and the species that lost the electrons got oxidized, and the species that gained the electrons got reduced. So let's take a look at this. So we're going to have to learn how to assign what are called oxidation states a little ways down the road. So we're not going to teach it just yet, but I just want to show you what these are. They're analogous to charges, and you guys are going to learn that any element in its elemental form is in what we call the zero oxidation state. So that's elemental sodium, and this is elemental chlorine as a diatomic. And so they're both in the zero oxidation states. So, and as part of an ionic compound here, these are simple monatomic ions, and sodium's in the +1 oxidation state, chlorine's in the -1 oxidation state. So again, which is kind of analogous to their charge as ions here. So if we take a look at this, my first question for you is whose charge or oxidation state, more properly, went down? Whose went down? And in this case, if you take a look, that's going to be chlorine. He went from 0 down to -1, whereas sodium went up from 0 up to +1. So the one that goes down, where its oxidation state goes down, that's what they actually term getting reduced. And so we'd say that the reactant, Cl2, got reduced, or we'd say that chlorine was the element that got reduced. So whether you just identify the element, or whether you identify the chemical species it's a part of, which in this case it just happens to be an element, so you say that the reactant got reduced. All right, so then if we take a look at the other side then, so sodium here went from 0 to +1, and in this case he got oxidized. And so we can see that to go from 0 to -1 and get reduced, you had to gain a negative charge, gain an electron in this case. And that's why reduction is the gain of electrons, or gaining electrons reduction, however you want to go with it. And it gets you more negative. And so this is weird because, you know, typically, like, if you gain something, you have more of it. So, and that's generally how it works. Like, you gain more money and your bank account goes up. But here you gain more electrons and your oxidation state goes down because you're gaining negative charges. And so it might seem a little bit backwards. That's why we're taking the time to really cement those definitions home. All right, so usually when I'm identifying the species that are oxidized and reduced in a reaction, I assign these oxidation states, and we'll learn how to do that in a little bit here. And then I look for the one that went down. And whichever one went down, that's reduction. And the one that therefore went up, That's oxidation. And most redox reactions are going to have one oxidation and one reduction. You got to have one, at least one of each. You can't have somebody losing electrons and nobody gains them. So you got to have both a loss and a gain of electrons. So there's always oxidation and reduction taking place at the same time. You can't have one without the other. Now it turns out in some more complicated reactions, you can actually have multiple species getting oxidized and or multiple species getting reduced all in the same reaction. But most of the ones you're likely to see in this course, you're just going to see one species getting oxidized and one species getting reduced. Probably not likely to see any of those more complicated ones. Okay, so a couple more things to define here. That's the oxidizing agent. And the reducing agent. The oxidizing agent we also call the oxidant. And the reducing agent we often call the reductant. So notice these are just kind of contractions of the entire term. Oxidizing agent, oxidant. Reducing agent, reductant. So that's kind of the way this works. Now, this is where things are going to seem a little bit backwards for a second, but we also identify certain agents. Now, these oxidizing and reducing agents are always on the reactant side of a reaction, never on the product side, so that's the first thing. So, but it's going to seem backwards here. So the oxidizing agent or oxidant gets reduced, and the reducing agent or reductant is the species getting oxidized. And we assign it like this just to confuse you. Not really. So there is a method to this madness. So let's say that you got sick of me, and so you tracked me down to my home and rang my doorbell, and I opened the door and you punched me in the face. So, and my question for you is, who got punched? Well, I got punched. Who did the punching? Well, you did the punching. And so notice the person getting punched and the person doing the punching are not the same person. Same thing here. The species getting oxidized and the species doing the oxidizing are not the same. So if we look here, we said that the oxidizing agent gets reduced. So if we take a look here, so sodium is getting oxidized, and if he's getting oxidized, we like to think of it as somebody caused him to get oxidized. Well, again, he got oxidized, he lost electrons. And so the question really was, well, who took those electrons from him? That's the way we want to look at this. Well, chlorine did. Chlorine gained those electrons. And so chlorine is the agent responsible for causing sodium to get oxidized. And that's why he's the oxidizing agent. In fact, we could say it that chlorine was involved in oxidizing sodium. So chlorine is the action here, and sodium is the one that's happening to, but you can do it the other way around as well. So we can say that chlorine got reduced. Well, who's the agent responsible for causing him to get reduced? So because chlorine getting reduced means he gained electrons, and the question then is, well, who gave them to him? So, and in this case, chlorine got reduced because sodium gave him the electrons. So sodium is the agent responsible for causing him to get reduced. So sodium is the reducing agent. So that's where they kind of, come up with these lovely names that initially seem backwards. So, but you got to know that the oxidizing agent, reducing agent are always on the reactant side, and kind of they seem a little bit backwards as far as who they are. So the oxidizing agent is the species that got reduced. In this case, Cl2 would be the oxidizing agent, and then the reducing agent is the reactant that got oxidized. In this case, that's going to be the sodium. One thing to know about the agents as well is you have to say the entire chemical species. It wouldn't be just enough to say, Na and Cl. Couldn't do that. You'd actually have to say, so who got reduced and is the oxidizing agent? Well, that's going to be the entire chemical species on the reactant side is Cl2. You couldn't just say Cl, you'd have to say Cl2. And then same thing over here, it's sodium. And it's, uniquely, in this case, it just happens to match up sodium because all we have is just plain old sodium. It's not diatomic, it's in its elemental form. So, however, we'll see some more complicated examples where we don't actually have just elements on the reactant side, we have like compounds. And when you name an agent, you have to name the entire compound. That's going to be important because when you just are assigning who gets oxidized and who gets reduced, you can identify an individual element within a compound, or you could just say it happened to the whole compound, and both are fine. But when you talk about the agents, it's the entire reactant species that you've got to identify. So now we're going to cover the rules for assigning oxidation states, and it's a little bit of a pain in the butt, and my rules are probably going to be different than a set of rules you're going to find in a textbook. And what you find out is that typically you're given a fairly generic set of rules in a textbook. to which there are numerous exceptions. So we're going to try and craft a set of rules that aren't going to have those same kind of exceptions. So this probably won't match any kind of textbook you're using, just an FYI. All right, so rule number 1 deals when you have an element instead of a compound, whereas rules 2 through 6 are all for compounds. So if all you have is an element, so then that element is in its elemental form, and it doesn't matter if it's a monatomic or a diatomic or even triatomic in the case of O3 for ozone here. So those are all elements in their elemental forms, and they're in the 0 oxidation state. No charge associated with them in one way, shape, or form. So that's rule number 1. Now, rule numbers, again, 2 through 6 are going to deal with you have compounds, or maybe in the case of ions in some cases, but those are usually pretty obvious. So in this case, we got magnesium chloride. Now we've got a compound. It's made of multiple elements. And so for a compound, we just skip rule number 1, which only applies to elements, and just move straight to rule number 2. And rule number 2 is going to deal with group 1 and 2 metals. In a compound, group 1 metals are always going to be +1, and group 2 metals are always going to be +2. And when I say group 1 and 2, keep in mind that that's on the periodic table on the far left. So your alkali metals are always +1 in a compound. Again, they could be in their elemental form and be 0, but if they're in a compound, they're always +1. And the group 2s are always +2. And so in this case, you got to ask yourself a question. So do you have any group 1 or 2 metals? So in the way this works, you just follow these rules in order. If rule 1 doesn't apply, move on to rule 2. If rule 2 doesn't apply, move on to rule 3. And so you follow them in order. And so once I realize I have a compound, I skip rule 1, go straight to rule 2, and I say, do I have any group 1 or 2 metals? And yeah, I do. Magnesium here is a group 2 metal. And group 2 metals are always +2 in a compound. Okay, so there we go. So it turns out once you've only got one element left that you haven't assigned an oxidation state to, you just jump straight down to rule number 6. And the last element you haven't assigned has to just balance out the charge. If you have a neutral compound, then it balances it out to 0. If you have an overall charge on your species, like it's a polyatomic ion or something, then you just balance it out to that overall charge. But in this case, this is a neutral compound. There's no charge listed up here, so we need to balance it out to 0. And for that to work, each individual chlorine would have to be -1. And so what you need to realize is that these oxidation states are always per atom. And so in this case, to balance out that +2, so that the overall compound balances out to 0, since it's a neutral compound, I need 2 chlorines that are each -1. And so if you said that the oxidation state for chlorine here was -2, that would technically be incorrect in how we define things. Now there is a total of -2 charge here to balance out the +2 charge here, but each chlorine is individually -1, and it's the individual atom's charge that we title the oxidation state. So here chlorine's oxidation state is -1. Okay. So moving on to the next one here, this is hydrogen peroxide. This is one of your common exceptions you would come across, it turns out, if you learned a generic set of rules. We're not going to learn a generic set of rules. So way this works, rule number 1 doesn't apply because that's just for elements, and this is a compound. Rule number 2, any group 1 metals or group 2 metals. Well, hydrogen is in group 1, but he's not a metal, so it doesn't apply to him. So then we go on to rule number 3. Rule number 3 is all about hydrogen, and hydrogen in a compound is +1. Unless you have a metal hydride, where it's just a metal and hydrogen. In that case, hydrogen will end up being -1, but you won't actually have to assign it. It'll follow through with rule number 6 in that case, it turns out. So, but hydrogen in a compound, typically +1, unless it's just a metal and hydrogen. Well, in this case, there's no metal involved. It's not just a metal and hydrogen. So notice in this case down here, we do have a metal and hydrogen and other stuff. And in that case, hydrogen is still going to just be +1. It's only when you have just, if it was just only a metal and hydrogen, that's when hydrogen would be -1, it turns out. But if you've got a metal, hydrogen, and other stuff, nope, hydrogen's still +1 there. All right, so hydrogen's going to be +1 in this instance for H2O2. And once we've done that, we just skip straight to rule number 6 because the only element left is oxygen. And so in this case, for this to balance out, I've got 2 H's that are +1 each. Well, then the 2 oxygens must be -1 each. Because again, this is a neutral compound. There's no charge listed off to the side here, so had to balance it out to 0. And it turns out oxygen in compounds is most often -2. And this is an exception. It's what we call a peroxide. A peroxide is when you have oxygen in the -1 oxidation state. And it's an exception. And if, again, most textbooks are going to give you some generic set of rules, and you're supposed to be like, oxygen is not -2, pretty much, except when he's not. And then they don't always give you the best rules for when he's not. How do you recognize a peroxide? It's not the easiest thing. Whereas if we follow the rules I'm giving you, here we just, assigned hydrogen first, and oxygen just had to balance it out and had to be -1. All right, so let's go to the next one here. So rule number 1, again, we skip, doesn't apply. We have a compound. We don't have any elements in their elemental form, so got a compound. Rule number 2, there are no group 1 or group 2 metals, so skip rule number 2. Rule number 3 deals with hydrogen. Well, we don't have any hydrogen, so skip rule number 3. Rule number 4 is all about transition metals. Well, we don't have any transition metals from the middle of the periodic table, so we skip rule number 3. We skipped rule number 4. And then so we move to rule number 5. And rule number 5 says the most electronegative elements get their standard oxidation state. So what do I mean by the most electronegative? So you recall back when we learned about polar bonds and stuff like that, electronegativity, fluorine, in the upper right-hand corner of the periodic table was the most electronegative element. And typically the closer you are to fluorine, the more electronegative something is. And so in this case, when you look at nitrogen oxygen, well, you got fluorine and then oxygen and nitrogen. Since oxygen's closer to fluorine there, oxygen's more electronegative. And so you're going to assign him first. And you're going to assign him his typical oxidation state. So, and then we covered this when we talked about naming and things of this sort. And so if you look at the halogens on the far right-hand side of the periodic table, they're 1 electron short from having a filled octet, which is why in compounds they're usually -1. So oxygen, sulfur, and selenium are typically, again, they're 2 electrons short of having a filled octet. And so in a compound, they usually gain those 2 electrons and have a -2 charge. That's what we mean by the typical oxidation state. And so in this case, oxygen's more electronegative. And so we'll just assign him his typical oxidation state of -2. Keep in mind that that typical oxidation state of -2 is going to supply an overall negative charge of -8. Now, the oxidation state is still defined as -2. I just want you to realize that because there's 4 of these oxygens, that's a total of -8. What that means then is that the last element standing, goes straight to rule number 6, is going to have to supply an overall total charge of +8, since this is a neutral compound. There was no charge listed over here. And so the question is, well, what does each nitrogen have to be to supply a total charge of +8? Well, there's 2 of them, so they must each be +4. And so oxygen's in the -2 oxidation state, and nitrogen's in the +4 oxidation state. Let's do another example. All right, so this is another funky example. This is called potassium superoxide, because it's super. And you're not going to get oxygen in his normal oxidation state. And again, it would be another exception that maybe you have to memorize. But with our rules, it's just going to naturally fall out. So we skip rule number 1. We move straight to rule number 2. So we got a compound. And rule number 2 deals with group 1 and group 2 metals. Well, potassium is a group 1 metal. And we're going to assign him the +1 oxidation state. And then we just jump straight down to rule number 6, since we only got 1 element left. And this is where things are going to be a little bit funky. So in this case, with potassium being +1, and let's put that in blue, just for the fun of it. Well, there's only 1 of them, and so it's +1. And so you need to supply a total charge of -1. And you've got 2 atoms to contribute to get a total charge of -1. Well, here's where things get a little bit strange. So the oxidation state is defined as -1/2. It turns out that O2 with a -1 overall charge is a polyatomic ion, a very rare one called a superoxide ion. And 2 oxygens, it turns out, share 1 extra electron, which is why on average they're both in the -1/2 oxidation state. So having a fractional oxidation state is not common, but it will show up at a couple places, and we'll see one other down at the end of the board when we get there. Cool, so just want to make sure you'd seen a fractional one, because every once in a while a teacher just likes to throw a trickster one on there, and they'll throw something with a fractional oxidation state. And if you've never seen it, you might just doubt yourself, even though maybe you did the process correctly. So, all right, next one here, sodium bicarbonate. Now we got lots of elements, and so it's a compound though, so we skip rule number 1, go straight to rule number 2. And do we have any group 1 or 2 metals? Yep, we have got a group 1 metal. So sodium's going to be +1 then. Okay, we still got 3 elements left though, so then move on to rule number 3, and we got hydrogen. And we have hydrogen, which is also going to be +1 here. And in fact, let me do that in blue as well. Let's do all the positives in blue and the negatives in red. All right, so moving on from there, we go to rule number 4, and deals with transition metals. We don't have any transition metals. Okay, so move on to rule number 5, and who's the most electronegative between the 2 elements that are left? Well, oxygen's closer to fluorine, and oxygen's more electronegative. And so we'll assign oxygen his typical oxidation state. And so we can see here that with 3 oxygens, that's going to contribute an overall charge of -6. Now with one sodium, that's just +1. With one hydrogen, that's also +1. And again, this is a neutral compound, so the question is, what does carbon have to be to balance this all out? Well, in this case, carbon's going to have to supply +4. And since there's just one carbon, well, then he is in the +4 oxidation state. That's the way that works. Okay, so another tricky example to look at here is NaN3. This is sodium azide. It's the explosive stuff found in airbags. So it turns into nitrogen gas and inflates that airbag really quickly. In this case, so skip rule number 1, move on to rule number 2, and we do have a group 1 metal. And in this case, group 1 metals and compounds are always +1. And then you just skip straight to rule number 6, and the nitrogen has to balance the rest out. Well, again, we've only got just the one sodium, I should say, and he's +1, so that supplies +1. And to balance that out, because there's no charge listed, so this must be a neutral compound, then we must supply a total charge of -1. But 3 nitrogen atoms get to contribute to that, which means they're each in the -1/3 oxidation state. And once again, we see a fractional oxidation state. And once again, for the same reason. So it turns out that N3 is a polyatomic ion called the azide ion, and 3 nitrogens share 1 additional electron. So that on average, they're in the -1/3 oxidation state. All right, finally we wanted to do one with a transition metal. So we've got this guy here, and if we look here, so we skip rule number 1 because we've got a compound. We don't have any group 1 or 2 metals, so skip that one. We don't have hydrogen, so we skip rule number 3. Rule number 4 deals with transition metals, and transition metals, you're usually going to assign them based on what they're with. And so if they're a cation, you're going to base them on the anion they're with, or if they're part of a polyatomic ion, you'll actually just treat them as part of rule number 5 and see who's more electronegative and assign them first. So, but in this case, so copper is with nitrate, and you can look at nitrate as a whole, and nitrate's a polyatomic ion, and it's got the -1 charge overall. And since there's 2 of those, and that's the total of -2 charge, well then copper must be +2. So notice I didn't actually assign any individual oxidation states over here between nitrogen and oxygen at this point. I just knew that the entire polyatomic ion was -1, and there's 2 of them, so that copper must be +2 to balance. Now, to assign nitrogen and oxygen, I know the entire polyatomic ion is -1 overall, but what is nitrogen's individual oxidation state and what is oxygen's individual oxidation state? Well, you've got 2 ways to approach this. You can solve it in the context of the entire compound, but that's not my favorite way. When you've got more than one of a polyatomic ion, a lot of students get confused and not realizing that you have 2 nitrogens and a total of 6 oxygens, and you got to factor all that in. Whereas the truth is, if you just pull one of those polyatomic ions out, like I did right here, there's the nitrate ion. Whether you have 1 of them or 1,000,000 of them, the oxidation states are going to work out the same. And so if I assign it over here, it's easier to do, and I can just apply it back over here. It's the same polyatomic ion, nitrate. And so in this case, between nitrogen and oxygen, so if I'm going through and assigning, again, no group 1 or 2 metals, skip rule 2, no hydrogen, skip rule 3, no transition metals at this point, skip rule 4. So, but rule 5 deals with who's more electronegative, and we'll assign him first, and that's oxygen. So we'll assign him with the -2 oxidation state. That supplies a total of -6 charge. And so the question is then, what is nitrogen going to have to be? Well, in this case, nitrate does have an overall charge. It's not neutral. And so we're not going to balance to 0 this time around. We're going to balance to -1. And so if you thought that nitrogen was going to need to be +6, well, that would have balanced us out to 0. And that's not what we want to balance to. We want to balance out to -1. And so we only want nitrogen to be +5. And since there's just the one nitrogen, he has the entire +5 oxidation state. And so it turns out oxygen's -2 and nitrogen's +5, and it works exactly the same way when you have more than one of them in a compound. So nitrogen, or oxygen I should say, is still -2, and nitrogen is still going to be +5. And if you look at the way this works out, so you got the copper, that's +2. You got 2 of the nitrogens, because there's 2 of them, that's a total of +10 more, and +10 + 2 is +12. And then you've got 2 times 3 is 6 oxygens that are -2 each, and that's a total of -12. And so like I said, whether you've got 1 nitrate or you have 2 as part of a polyatomic ion, or 3 or 4 or whatever, so it'll work out the same. And so my personal favorite is just to pull it out. So, and the big key though, that when you've got a polyatomic ion is instead of balancing it at 0, you're going to balance to whatever the overall charge is. Cool. This is the rules for assigning oxidation states, and I highly recommend you just keep these rules handy and go work a half dozen examples. And then hopefully after that half dozen, kind of put the rules off to the side so you don't use them and try another half dozen and see how it goes. Now, if you found this lesson helpful, would you consider giving me a like and a share? Pretty much the best things you can do to make sure that other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you're looking for oxidation reduction practice problems, check out my premium course on chadsprep.com.